Vectors in the plane. Previously, we talked about what it means to graph a vector and different vector operations. Now I'd like to talk about properties of vectors, such as length. Let's start with a vector v with components v1 and v2. We'll let L denote the length of a vector. Sometimes we also write the length of a vector with double bars. Kind of like absolute value gives you the magnitude of a number, double bars give you the magnitude or length of a vector. So I have my vector v. I'm going to draw it in standard position. So its initial point is at the origin, and its terminal point is at the point v1, v2. What I'm interested in is calculating the length, L, of this vector. Now I'll take this vector, and I'll drop a line from the point perpendicular to the x-axis, and I have a right triangle with sides v1, v2, and L. Because I have a right triangle, I can use the Pythagorean Theorem to calculate L. The Pythagorean Theorem says that the sum of the squares of the sides is the square of the hypotenuse. v1 squared plus v2 squared equals L squared. So I can solve for L. L is the square root of v1 squared plus v2 squared. So that gives me a formula to calculate the length of a vector. For instance, if the vector v is given by 3, 4, the length of v is the square root of 3 squared plus 4 squared. And that's the square root of 25, which turns out to be 5. Lengths are often not whole numbers, but that one was. Now, some properties of the length of vectors. What if you take the scalar multiple of a vector v? That is, c times a vector v is c times v1 and c times v2. What effect does that have on its length? Well, we'll just use the formula. It's going to be the square root of the squares of each component. And after distributing through the square, I've got a c squared on each term, so I could factor that out. The length of c times v. And now, bringing out the c squared through the square root sign, I'm left with the absolute value of c. Very important in case c was a negative number. You notice what's left under the square root sign, that's actually the length of the vector v. So, if you have the length of c times vector v, it's the absolute value of c times the length of v. Which is an algebraic fact that agrees with our earlier intuition that scalar multiplication really did just scale a vector. Now occasionally, we'll be interested in unit vectors, that is to say, vectors which have length 1. We won't be interested in how long it is, just the direction it's pointing. So given a vector v, what we'd like to do is create a new vector, a unit vector, a vector that points in the same direction as v, but has length 1. I'll call my unit vector u. The question is, how do you create a unit vector? Well, let's say L is the length of the vector v. Then the unit vector, pointing in the same direction as v, is going to be scalar multiplication of 1 over the length times the vector v. Now to check that this works, we want to check that the length of u is really 1. Well, the length of u, by definition u is 1 over L times v, and we know by our earlier property that if we're doing scalar multiplication, we take the length of that, we can pull out the scalar multiple, as long as we surround it by absolute value bars. We have 1 over L times L, which is just 1. So, the length of u is in fact 1. To find a unit vector, just divide a vector by its length. So we'll do an example. Let's say we have the vector 3, 4, and I want a unit vector pointing in the same direction. We know from before that the length of the vector v is 5. So, a vector pointing in the same direction as v, but having length 1, is the vector 1/5 times 3, 4. In other words, 3/5, 4/5. To see what's going on, it often helps to draw a picture. If I draw the vector v, draw it in blue, and I'll draw the vector in standard position, v is the vector 3, 4, and that vector has length 5. The unit vector u, which I've just calculated, I'll draw here in green. It points in the same direction as v, but the length of this vector is 1. I have many occasions where we want to convert a unit vector. We want to convert a vector into a unit vector. Now another thing which will be useful is sometimes instead of given a vector to convert into a unit vector, we look for a unit vector in a direction theta. And what that means is, if we draw an xy plane, we want a vector that forms an angle of theta with the x-axis. And we want that vector to have length 1. The question is, how do we find the components of that vector when all we're given is the angle? A little bit of trigonometry comes to the rescue. Again, I'm going to take the terminal point, drop a line perpendicular to the x-axis, and I have a right triangle. Now I've got the side adjacent to theta and the side opposite from theta. We're going to use a little bit of trigonometry. Remember, to calculate sine of theta, it's the length of the opposite side divided by the length of the hypotenuse. To calculate the cosine of theta, it's the length of the adjacent side divided by the length of the hypotenuse. Since the length of the hypotenuse is 1, the length of the adjacent side is just cosine theta, and the length of the opposite side is sine theta. So the unit vector, in order to go 1 unit in this direction, I need to go over by cosine theta and up by sine theta. Now to check that this is in fact a unit vector, I need to calculate its length. So length is the square root of the sum of the squares of the components, the square root of cosine squared plus sine squared of 1, but that's the square root of 1, which is 1. It works out well. For example, let's say we want to calculate a unit vector that forms an angle of pi over 4 radians, or 45 degrees, with the x-axis. Well, to calculate the components of that vector, I need to know cosine of pi over 4 and sine of pi over 4. And that, it turns out, is rad 2 over 2, comma, rad 2 over 2. That's the unit vector in the direction pi over 4. What else might you need to do with vectors? Well, we know how to calculate unit vectors in a given direction, but perhaps we'll want to calculate just a vector in a given direction. For instance, a vector of length 3 that forms an angle of pi over 4. So now we're given both the direction and a specific length. The length might not be equal to 1. The way we would calculate this vector is the length that we want times the unit vector in that direction. In other words, it's much like the previous problem, except we want to take our unit vector and we want to scale it so it has length L. So in other words, we multiply each component by L. We should do an example. So let us say we want to calculate a vector that forms an angle of pi over 6, or 30 degrees, with the x-axis, and has a length of 5. I'll draw a picture of what it is I'm trying to calculate. It's my xy axis. And I would like a vector that forms an angle of pi over 6, and the length is 5. I would like the coordinates of this point. Call it V1 and V2. So all I have to do is calculate the unit vector and multiply both components by 5. So I'll have 5 times the vector cosine pi over 6, sine pi over 6. Now cosine pi over 6, that's one of those that you might remember is rad 3 over 2. Sine pi over 6 is 1/2. So, multiplying this through, I get the vector 5 rad 3 over 2, comma 5 over 2. That's the vector, which has those properties. Now from time to time, we'll need a few special unit vectors. The vector I, that will always denote the vector 1, 0. And the vector j, that'll always denote the vector 0, 1. These vectors point in the positive directions of the x and y axis. And any vector can be written in terms of these unit vectors. For instance, I could take v1, v2 and break it up using vector addition. And then, using scalar multiplication, again, I could rewrite each of these vectors. v1 times 1, 0 and v2 times 0, 1. And remember, 1, 0 is the vector I, and 0, 1 is the vector j. So you can write a vector in component form, where you just list the components, or you could write it in terms of the unit vectors I and j. Occasionally, this notation will also be useful.